All right, so today we're going to go over the basics of hypothesis testing. We're not going to do everything in detail. We're just going to give you a general idea of what it's about. You will probably want to take notes on these, and later on we'll give notes on some of the specifics. So first off, hypothesis testing can be very confusing. An example is one of the concluding sentences you might state, like failed to reject the null hypothesis, a triple negative. So expect your brain to hurt sometimes, and that's fine. It will fall into place as we go. All right, so why we use hypothesis testing? We're bringing this up now because there's always that question of how do you determine when new discoveries are actually really discoveries or just a random occurrence? We can see this when there's new drugs on the market, for obesity, heart rate, all those things. How do we know that it's not just like randomly worked these couple times or that it truly is something better? All right, so an example would be if you came up with a new drug for balding. Does it really work rather than regular shampoo? How can we really see that beyond looking at the samples? And so we do some math to check this out, and that is called hypothesis testing. All right. So to do hypothesis testing, you need to remember three things that we have covered before. So I just want to remind them to you real quick. Give you a reminder. One is the normal curve, one is find the probability using the normal curve, and the third is standard deviation. So let's just go through these real quick. If you don't remember them, you might want to write these down. First one is your normal curve, just your notation. It's n, and then you state the mean and the standard deviation. Your mean is in the center, and then the units that you push out, you count out are in standard deviations between each tick mark. All right. That's the normal curve. Now p-values. P-values are the area under the curve, the probability of seeing a specific value. So in this example, we're going to be looking at 1.13. What's the probability of getting 1.13 or less? So I do say less because I'm shading this whole area here. So if you remember, we use normalcdf to figure this out, and we get this number, which will turn into a percent. And when you do that, you end up finding that there is an 87% chance, that's this number turned into percent, of observing a value of 1.3 or smaller. All right. Another example would be, say you want to look at an exam. Okay, so we want to find the probability of getting a score of 70 or lower when the mean is 55 and the standard deviation is 10. All right, so we make our normal curve here, and there's our notation. And when we do that, what we find is that we want to find that percent that of the gray area, that or lower. So we use normal CDF, the mean, the standard deviation. Then you put your lower bound and your upper bound, if you remember that, which would be these guys, and we do all that, we get 93.32%. So your chance of getting a 70 or lower is quite high. All right, the third thing you need to remember, just because you might be like, how do I find the standard deviation? Well, often I give it to you, but with proportions, you got to find it on your own. So proportions will give you P, the proportion, the chance of becoming bald or the chance of having blue eyes. And then you need to find the standard deviation using that P and this equation right here. So hopefully this sounds familiar to you. All right, those are the three things you need to know. Once you've got these three, we can start with hypothesis testing. Now, hypothesis testing is generally going to involve four things. First, and this is the most confusing, you need to decide your cutoff probability, and that's going to sound really weird, but hopefully as we do more examples, it will make sense. And what that really means is you need to decide when I look at the probability of a new drug working, what's the probability that I just get those results randomly versus the probability that it actually happened, and I kind of compared those two. I know what I just said still sounds vague, but I think just give it time and it will clarify itself. So what we do second is we state the hypothesis for what usually happens. So we first want to look at the status quo, and we call that HO. That's the notation right here, HO, and it's the null hypothesis, the status, that's misspelled, the status quo. Then we also state the alternative hypothesis. That's based on your new findings, okay? So say the null hypothesis for balding is you lose 100 hairs a week. All right, that's just what always happens. That's the status quo of men over 50. Okay, they lose 100 hairs over a week. The alternative hypothesis, that's going to be your new findings based on that new drug you're using. And maybe the new findings is that you lose less than 50 hairs a week. Okay, so status quo versus your new data, HO and HA. Then we use a normal curve and the p-value to determine the probability of this actually happening when the status quo is going on. So in the normal case, when most men over 50 lose 100 hairs a week, what's the chance that they observed that this randomly happened, that randomly some guys only lost 50? So we're going to look at that, determine that probability, and we use that using the normal curve. Once we find that probability or that p-value, we do our conclusion, which is we decide to either retain HO and say, you know what, we think that it's still just the normal thing and it's randomly a couple guys lost less hair, or we reject HO and we say, oh my gosh, there's such a small chance of seeing what we saw that it must be true. This must be a new discovery and a great new drug for balding. So what this is, hypothesis testing is a lot like a court case, okay? You're innocent until proven guilty. Innocent being your null hypothesis, guilty being the alternative, okay? So if we look at that, we have innocence as our null hypothesis. So we have this guy in court. He's assumed to be innocent. The null hypothesis, and that is our status quo. That's how people start off in court. That's how testing starts off with the hypotheses testing. Guilty is your alternative hypothesis, okay? So if the lawyer showed this photo of the man, he's saying, well, actually, alternatively, he could be guilty. And we will reject HO in a courtroom when innocence is highly unlikely. You might have heard the term guilty beyond a reasonable doubt. All right. So again, the alternative is your new findings, or in the case of a court, being guilty. So basically, in statistics, we are like a courtroom. Our evidence is the data, and we measure how likely the data is to occur using the p-value. So let's look at another example. Let's look at an example for a drug to lower heart rate. All right, so a new drug comes up to lower heart rate. The new drug claims to keep heart rate below 35 beats a minute. Okay, and the data that they have for that is they looked at 45 patients using a drug, and their mean was only 33.6 beats per minute. Okay, so the status quo here is 35 beats, and we want something that would make you lower that. So as people get older, they actually kind of want it. They don't want their heartbeat to be too fast. So we want to figure out, did this just randomly happen for these 45 people, or is this really a new discovery? So to do that, we need to measure how likely we are to observe the new data using p-values, okay? And to do this, we have to first come up with that probability. That was at step one. We have to come up with a critical value, and a common one is 5%. All right, so I'm going to say that if the probability of seeing all these things is greater than 5%, then I'm going to just stick with the null hypothesis. However, if my p-value is less than 5%, I'm going to go with the alternative hypothesis. So that would be in a courtroom, innocence or guilty, and then for ours, it would be rejecting or accepting the new drug. So if we're likely to see it, p is greater than 5%, we stick with the null hypothesis. And if there's a really small chance of seeing what we actually saw, then we go with the alternatives. You want to keep this in mind. And again, the other thing I want you to keep in mind is that this 5%, we can change it for different scenarios. All right, so it claims to increase the heart rate. Step one, we choose the critical value. For us, we've chosen that critical value, also known as alpha. That's our symbol for alpha, of 5%. That was the first step. Okay, so we know that we want that area to be really small if we're going to accept it. We then state our null and alternative hypothesis. So the status quo is a heart rate of 35. The alternative is that it is less than 35. Next step is we make a normal curve and find the p-value. All right, I went ahead and did this, and when I did this, I got a p-value of 0.0068. I will later go into details of how to do this again with you. But for now, that is my p-value. Now that is pretty small if you think about it. I turn that into percent. That's less than 1%. Step 4, I see if the p-value in the null or alternative hypothesis is in the range that we talked about earlier. All right. So with a p-value of less than 1%, I would actually reject the null hypothesis. All right, so that ends up with a 0.68 chance of getting 33.6 beats. Does a new medicine work to decrease the heart rate? Well, here's what you're looking at. Is this 33.6 heartbeats just expected variation from the normal heart rate? If it's expected, that sometimes happens. Randomly, people have a lower heart rate. As I said before, we just retain the null hypothesis and say, we're not going to invest money into this new drug. It's nothing really new. However, is this 33.6% beat so surprising and unexpected that just the fact that it happened is evidence that new results are true? Okay, and in this case, when something occurs that has such a small chance of happening, we are super surprised and we say, oh my gosh, we shouldn't have seen this. It is such a small chance of happening that it must be different. This must not be happening under normal conditions. That status quo is not the case anymore. We actually have a drug that really does lower heart rate and it is worth investing in. We're going to take on and adopt this new drug. All right, so retaining or rejecting the null hypothesis, you just simply answer that question. Is the p-value significantly small? Determine what is small depends on, well, that alpha, what is the critical value. In our case, for this last one, we did 0.505 or 5%. As I told you, sometimes you choose a different cutoff. Okay, depending on the situation. Often with safety and medical, we want to really careful, so we choose a really low cutoff of 1%. When you're looking at like people's preferences and stuff, and this is often a very common standard in research, we do 5%. If the issue is little importance, maybe a 10% cutoff. All right, the most common definitely is 5%. So if P is less than 5%, we reject HO, and if P is greater than 5%, we retain it. So I hope that makes some sense to you. We're going to do some problems now, try to get a better feel for this, and we will go into more details later.